Ralf. I'm a software engineer at Square. I've been at Square for about a year now. And the reason why I wanted to give this talk is before I joined Square, I worked for smaller companies, startup size, sometimes 50 people, sometimes 300. And I always wondered how those bigger companies deal with the issues that I have at my company. And do they run into the same issues? Do they also have slow builds? How do they deal with it? How do they develop features? How do they ship products? And I really hoped all the years that someone would give such a talk and explain me how they do it. And nobody did. So I hope with this talk that I can give you a little bit of an insight. I try to keep the description of this talk rather generic because when I submitted the talk, I didn't really know what I should be talking about yet. And I can only give you a glimpse of an insight how we work. And I try to focus on how we structure code and how we split up features. But before I start, let's go a step back and look at how most companies start. When we start a new project, we usually start by creating a new application module. And then we start developing features, and we do this fast because we want to ship fast. And we add features, we add common code, utilities, and this is all fine and expected, and our application grows. And stay there, we don't run into any issues. The first issue comes, however, up if a company decides to ship a second product because maybe they want to have an app next to it or a smaller subset only of the features. We then, as software developers, we don't want to reinvent the wheel. We want to share code. We want to reuse what we've already developed. So we start extracting the common code into a library and reuse this in both applications. But that's not the reality what we ship. In reality, we ship two fat binaries. And that's not really what we want. We want to ship one tiny application because that was the goal, having a tiny app, and one bigger app. So we go back and we start breaking up our library module into multiple libraries. And in the middle, we have this hairball, this kind of thing, which really is the old code that we extracted that is really tangled. We don't know how to separate it into smaller pieces. That's what we really had at Square for 2 years. We've been working on this to breaking it up into smaller pieces, and it was a big problem. And here we also need to start to think about how we structure those libraries. We need to have a structure and some kind of hierarchy. And then I often see at many companies that they have something like this, where they have a common directory with common utilities, then they have a feature directory, and then they have rules like common code is not allowed to depend on feature modules, and other features are not allowed to depend on other features, and so on. And I'm honestly not really a fan of this because it causes more problems than it helps, in my opinion. For example, what is login? Is login a feature or is it common code? Other features depend on login and on the account status. So should it be common feature? I don't know. And also the hairball, it doesn't really fit into in this picture. The hairball contains features, but also common code at the same time. So what should we do about it? I think you can guess it that the picture I showed you wasn't really the reality what we had at Square. The reality looked more like this, and it's kind of scary and messy, and it makes onboarding new developers really hard. It's not really important to you, but 2 weeks ago, we were finally able to kill the hairball, and it removed 2 layers of our architecture. And this was a big success for us because we were working on this for so long, and so many developers contributed to this goal. And we are happy that we finally achieved it. But we are not done with this. Modularization is an ongoing process. We still have other smaller hairballs that we need to break up. So modularization never stops. But at the same time, it's also important to celebrate these moments and see what you achieved and when you reach milestones. So let's go back to the example. Then when you start breaking up the hairball, you extract more and more libraries. So your repository grows and you get more of these library modules. Then also the question comes up, where should you put those libraries? Should you create a new repository for each of them, or should you have a mono repository? And I want to stop here because this could be a talk by itself. There are several advantages of having multiple repositories or using a mono repository. We at Square, for the Android code base, have a mono repository. And I'm really happy about this. The only exception is Cash App. That's a different product, but otherwise in the register code base, everything is in one single repository. And it was a good decision because if we look at how the number of modules grow in our code base, then you wouldn't be able to manage this with multiple repositories. So everything is in one, and there's a steep increase in the number of modules we have, and we don't see a reason why this should slow down anytime soon. And this is not also only because we are breaking modules, bigger modules up into smaller ones, but we're also writing a lot of code. And this code lives in the repository. It's what we ship in the product. So there's a reason why the size in our repository is growing. At the same time, we are looking at another really important metric to us, and that's the average size of a module. We want to keep the modules rather small than big. And so it's a nice trend to see that the average size of a module is going down. Because in reality, the weight of a module, it matters. We ship multiple products, and for smaller applications, we ask ourselves, we need to ask ourselves whether you really want to depend on a module. Because there are modules that are rather heavy and have a lot of transitive dependencies. Some of them contain a lot of code. So it plays a factor in the end for what you ship. And we tried to make sense of this mess that we had, and we wanted to introduce some structure. And often in these cases, it helps to go a step back and think about what you're trying to achieve, what you're working with. And one of the questions was, what is actually a module in a modular design code base? Well, a module is supposed to be a self-contained piece of the whole system. It's a logical unit, and it performs some kind of work. And ideally, this module does only one job, and it does this job well. We try to have loose coupling. That means if I change a module in my entire system, ideally, I wouldn't need to change any of the other modules. At the same time, we are aiming for high cohesion. Cohesion means that everything inside of this module is only there in order to do this one task and nothing else. Let's say, for example, I have a module which has 2 independent features. Then the cohesion level of this module is low, and it would be a good candidate to be broken up. One really famous example is a utilities module. Utilities are terrible for modularization because so many other modules depend on the utilities, so the coupling is really high. And also utilities often contain a lot of independent functions and utilities that you want to share. And so the cohesion level is really low. So utility modules are usually terrible. Why do we want modular design? Well, there are many advantages of it. The code tends to be more reliable because it's easier to test. It's also easier to maintain with the goal. When you make one change in a module, you only have to think about this module and nothing outside of it. Another really important pattern that we rely on at Square is dependency inversion. I could give you a dry explanation what dependency inversion is. You can look it up at Wikipedia, but I want to show you at a concrete example. Let's say I have this class feature which accepts the post login strategy argument, and then post login strategy is a separate class. This is not great because we have really high coupling between those two classes. And it's likely that when I change my post login strategy, that I also need to update my feature class. The solution there is to invert the dependency on the class by introducing an interface, which I call here login strategy. And my feature class accepts now this interface, or an instance of this interface as an argument. And then my post login strategy implements this interface. Now this allows me to make changes in the post login strategy, and my feature class doesn't have a dependency on it directly. So it is very likely that I don't need to update anything there. And that's what we rely on heavily at Square. Of course, then the question comes up, do we need dependency inversion? And it's a valid question because for dependency inversion, you tend to write more code. Not only do you have to introduce an interface, but you also have to wire the implementation to the interface in some way, whether that's Dagger or you do the wiring yourself, but it has to happen. So do we really need dependency inversion? Let's say in our case where we ship multiple products every 2 weeks. And the clear answer is yes, you definitely want dependency inversion because we want to swap implementations for different products. For example, some of our apps, they don't use or cannot use Firebase, and we want to use our own push message implementation. Whereas apps that we ship in the Google Play Store, they can rely on Firebase for push messages. What happens if you have multiple modules, but you only ship one product? So you have a modularized code base, the example that we had in the beginning. Even then, you should use dependency inversion in order to break up coupling between the modules. What if you only have one single module? Remember from the beginning, this one gigantic application modules. Do you need dependency inversion there? And here I would argue, yes, even in this case, you need dependency inversion. Think of your tests. In Android instrumentation tests, you often want to replace the network stack by fakes and mocks. And in order to achieve this, you need dependency inversion, and you're not supposed to hard code the concrete implementations. And what if you don't write any tests? Then, well, I hope it's only a hobby project, but when the project grows, you will help yourself for this decision. If we go back to our example, this is how it looks like. We have this login strategy interface. We have the concrete implementation, post-login strategy, nothing special there. And I've seen this pattern quite a lot at Square, where we put this Dagger module right next to the application because it makes it easy to use. I later just have to include this module somewhere, and then I don't have to worry about the concrete implementation anymore. But I really dislike this pattern, and it caused a lot of problem for us because if you think about it, the implementation often doesn't look like this. It looks more like this, where I inject multiple objects. And this is fine and expected because we want to reuse code and not re-implement everything from scratch. And I looked at the biggest class in our code base, and I found one candidate that injects 40 objects. So this could get messy. So what does this do with our dependency graph? Well, when we want to reuse logic, we have to import all those libraries. And again, this is kind of expected. But what happens if we want to consume this library? Let's say I want to reuse this login strategy in my feature class. So that's what ideally would hope for. But the reality is that I get this because post-login strategy and the interface itself, they are in the same module. So I have to import both. I don't have any other choice. So I added dependency in my feature module on login strategy. That's what I want to have, but the reality is this. I get all those transitive dependencies, and this is terrible for modularization. And this was a big problem for us when I started at Square, and we had to look for alternatives. And at the beginning of this year, we decided for a new module structure, which should solve these problems. And the idea here in our new module structure is that we separate the API from the implementation and from the wiring code. And we do this by introducing a new module. Every library has a public module. And in this public module goes in the API, like the interfaces, but also the data types in some cases. And then we try to move all the implementation details into the impl module. And then our Dagger modules, they go into the impl wiring. So they are separated from there, from the implementation. All these three modules live within our library module, which is login strategy. And then in Gradle terms, the module names would look something like this. I think you guessed it. That's not really the reality that we have at Square. The reality looks more like this. And it's not that complicated. We still have our public module and our impl. And at the same time, we have a fake module. Fakes, think of them as a separate implementation for the API. But in our case, they have some special rules. For example, our mock implementations for our retrofit services, they go into a fake module. And we use them in order to use the mock mode at runtime. On the side, we have a testing module. There we put not our tests, but the utilities that help you to write unit tests. Let's say you want to reuse a module and you want to have fake data in your unit test later in the other module. So this gives a library the option to share these test utilities. At the bottom, we have our robots. There was a good talk about Jake Warden about this, about how we use test robots. And they serve as an abstraction between the concrete implementation and your UI tests. So that in your UI test, you don't have to reference any resources or resource IDs or string IDs. Instead, you call your robot. And the advantage is that when you change your implementation, for example, the resource name, you only have to update the robot and not all the hundreds of tests. And then we have a demo module, which I will talk about later. Let's go back to our example and how modules should be reused in this new structure for us. This is kind of the expected. You're all supposed to import only the public module, the API. And it is allowed that for other public modules to import other public modules. But we try to avoid this nonetheless. If you think about it, and a public module describes the API of this library, what this module is doing for you. And often enough, you don't need to know about dependencies. One good example is analytics. Let's say I implement my login strategy. Do consumers need to know that I use analytics internally? Not really. That's an implementation detail. So we try to achieve or try to do this, that our implementation modules import other libraries and reuse code this way. And the advantage is then here, if somebody uses my public module, they don't see any of my transitive dependencies. But the most important rule is in our code base is that no implementation module is allowed to depend on another implementation module. You're always supposed to import the public module. And this allows us to swap implementations for different applications without changing the code. So that's the only thing that you should keep in mind. We introduced the module structure at the beginning of this year. We didn't do a strong push for any adoption or like this, but developers at Square picked it up nonetheless because it's so easy to reason about where you need to put your code and how you separate the API from the concrete implementation. But nonetheless, it's an ongoing process, and we still have legacy modules in our code base, and we have to deal with them in the new world. And the simplest solution there is, and it's the only solution that we found, is that all the rules that we have for the new module structure, they don't really apply for legacy modules, because legacy modules are the public impl and the impl wiring module in one. So you cannot have rules like impl isn't allowed to depend on impl. But it doesn't mean that you shouldn't think about dependencies, because they are important. So what did we really achieve by doing this now? Well, we separated the API from our implementation. The implementation needs to depend on the API because it needs to know what it implements. And we also separated the wiring. And it is really clean to separate these concerns, because in other cases, you use a different wiring mechanism. For example, we at runtime, we rely on Dagger. Dagger generates all the wiring code for us. But in unit tests, we call the constructors manually. So we write the wiring code ourselves. So separating those three concerns is really clean. Now back to our example, it should be clear by now that the login strategy, the interface, is supposed to go into the public module. The concrete implementation goes into the impl module, and our Dagger module goes into the impl wiring. If we look at our dependencies, this is what we used to have. But by separating these concerns now, I can import a public module and I don't get any of the transitive dependencies. And it's a big achievement for modularization and isolation. The dependency hierarchy that I mentioned earlier, that sometimes doesn't really make sense. We don't need it anymore. All we need is really a shared folder. And inside of the shared folder, we have a flat hierarchy of libraries. So it is expected for modules to depend on other public modules. But below the public and the impl module, there would be only really the wiring and then finally the application module. So your dependency hierarchy is much flatter. The other really important piece in our code base are development apps, and they sit right below the impl wiring. Development apps are the idea that you take any feature out of our application, you put it into a separate application, and you run this application in isolation. And that's what you usually see when you create a new development app at Square, you see the login screen, and then in the debug drawer on the side, you can log in, and then you see a feature on the screen. If we wouldn't have development apps, how would we create features these days? Well, we would start with an empty feature module. We would need to start to integrate this feature module into the main application. We have a release train every 14 months where we ship the application. So we have to hide our non-implemented feature behind a feature flag until we finish it, and then we can turn it on. And this is a problem because before you actually can start working on a feature, you have to do all this other nonsense like the integration, which takes a lot of time. But you only really wanted to start working on the feature. And development apps really skip this whole process because you create a new feature module, you create your development app, and you can start writing code in your development app. And when you are confident that you are ready and to ship this feature, you can start doing the integration into the main product. Think of development apps also a little bit like the test-driven approach. In test-driven development, you write the API, you start writing tests for this API, and then you keep iterating on your implementation until it passes your unit tests. And development apps are kind of similar. You start writing your feature, you see maybe a placeholder on the screen, and you keep iterating until you see the final result. Development apps have other benefits, like you get shorter build times. You don't need to build the entire product over and over again. We are having millions of lines of code in our repository, and you can imagine that it's quite slow to compile the app. So development apps have this big benefit. The other thing is that you launch into the feature directly. You don't have to navigate through the whole application first. Instead, you see your feature right on the screen. We also want to write our UI tests against development apps, and only the main product should run some full integration tests, but not test the features themselves anymore. This has advantages like the UI tests are better isolated because you replace dependencies by fakes, and it is less likely simply that UI tests fail because of fakes then. Another really important component at Square is our workflow library that Ray and Zach gave a talk about at the droidCon in New York City this year. It makes it also possible to write development apps easier for us. It's not necessary, but it certainly helps. Think of workflows for now as a controller that sits between your UI and your business logic. And it's a unidirectional data flow library because, well, that's Ray always says it like this because it's fancy and hip right now. So there's one stream of events that's going out, which is rendered on the screen, and another stream of events is going into the workflow. And I want to show you how the process looks like at Square right now when you want to create a new development app. Let's say we want to write a login screen. And after you finish the login, you want to show the account screen. So our login screen module needs to depend on the account screen. So, and I told you earlier, we are supposed to import only the public module. What do we really need to know about the account screen? Well, that's all we need to know. We know it's a workflow. A workflow has an input type, which is unit in this case. It has an output, which is also unit. We don't really care about it. That's all we really need to know. And then we can go ahead and reuse this interface and then implement our login screen. This happens in the login screen module, and this is the concrete implementation. The implementation isn't really interesting. The only thing that matters is we build up navigation by reusing and injecting these workflows, which I do here. I inject the account screen workflow. And again, this is the interface, not a concrete implementation. And then when I finish my login, I probably want to launch this child workflow and render the child workflow on the screen. When I create my development app, I need to have a concrete implementation. I want to test my login screen, not the account screen. So it's certainly helpful to replace this dependency by a fake. And that's what I do. Inside of my account screen module, I create a fake module and implement the interface. And implementing the account screen workflow interface is simple. It's basically a no-op. I do nothing else. Then I can go ahead and create my login screen demo module. And this is almost how build script looks like for us. We have scripts that handle all the boilerplate for you. We also have tools that generate all the modules for you, so you don't have to copy paste anything. Everything is generated. But the important piece here is that we make a decision here. We decide in our application module that whenever we inject the account screen workflow, that we get the accounts or the fake account screen workflow. And we try to push this decision, which implementation you are using finally, to the bottom, to the application modules, because everything above, all the library modules, they shouldn't really care about which implementation you use. You make this decision for the product that you want to install and run on. And what did this do to our dependency graph by using the fake implementation? Again, in our login screen module, we had the dependency on account screen. And let's imagine we would have used the real implementation that we ship in our final application. Well, then we certainly would need to have a dependency on the impl module. But the problem of the impl module is that it has other dependencies. Let's say the real implementation, after you see your account screen, there's an edit button and you can change the account details. So our account screen module, the implementation, has a dependency on the edit account screen. And the edit account screen lets you change the photo. So you have a profile photo screen, but you also have a dependency on the camera because you want to take a new photo. So we would get all of these dependencies that we don't really care about in the login screen. We only cared about the account screen because we want to render something on the screen. And by using the fake module, we get rid of all those dependencies. And that's what helps us to reduce the build times because, well, we need to compile less code. So fakes have this nice side effect that they reduce the size of our dependency graph, and they also reduce the size of the lines of code that we need to compile. And this is, for example, important when we make a change in our utilities, because everyone depends on utilities. It sometimes is almost like a clean build. And by compiling less code, you see things, and especially your feature, faster on the screen again. And fakes also have the nice side effect that you can change their behavior. You can say what they are supposed to do and how they, what they should return. So you can test rare cases that are otherwise hard to reproduce in the final application. You can control the fakes and simulate the scenario. I was talking about build times a little bit, and I wanted to show you this graph, how the build time evolves for us. We are creating more and more new modules, and we are writing also more code. So evidently, our main product takes more time to compile. And that's what we're seeing here. It's getting longer and longer. At the same time, with development apps, we were able to keep the compile time or the build time down to less than 10 seconds. And that's a big achievement. If you want to make changes, see something on the screen, change it again. If you want to iterate fast, you cannot have these long build times. I know you also might be wondering, why is there this big spike? And the reason for this is that we had a memory leak in our build, and a colleague who's sitting there found this memory leak and fixed it. But we're also relying on another tool, and that's the Gradle profiler. So if you want to benchmark your build, don't just start a build and measure the time with a timer. It's not working well. You really need to have a tool that warms up your Gradle daemon in order to get consistent results. And the best tool that's out there, that's the Gradle profiler. So I highly recommend that you check it out. This is another graph of our build time. Here again, we see that our main product, the numbers don't really matter, but we were about 4+ minutes. And after we fixed the memory leak, we got down to 3 minutes. But there was more room of improvement. And we used the Gradle profiler to test several settings, memory configurations, heap sizes, experimental Kotlin features. And we were able to get the build time down to almost 2 minutes again. And this is huge because not only if you spend the time and focus on your build, not only you benefit from it, but also your colleagues. And in the long run, it saves a lot of time. And usually people start thinking about build time when it's too late, when it's already taking too long. And I would really suggest prevent longer build times early in the process, because it will save you a lot of time in the long run. And that's almost all I got. What is the takeaway from this talk? Well, I hope you have seen that Square isn't really different. We also have our problems and issues that we need to deal with. At my old company, we also had our issues. It's somehow similar. The scale is only a little bit bigger. Modularization is an ongoing process, and I don't think we will ever finish it, because you add new code and requirements change. So it's never done. But it's also important to celebrate these moments when you make progress or when you reach a certain milestone, like we did when we killed the hairball. Start thinking about dependencies and your build time earlier in the process. Dependencies play such an important factor for your build, and you shouldn't just add a huge dependency because you want to reuse one method. Think about how you would break up these modules and how you structure your modules. And it's, again, important to reuse design patterns. The design patterns often make things so much easier to think about. In our case, it was dependency inversion. And we really implemented the dependency inversion pattern in our module structure by separating implementation from APIs. And this makes it easier also for new engineers during the onboarding process. They don't know our code base, but they might know the design patterns, and it makes them so much, or saves them so much time to get used to the structure that we use. Yeah, that's all I have, and thank you very much.